Okay, good morning. We'll go ahead and get started. A couple announcements. So your exam 0 has been graded. Thank you to those of you that reached out to me. I noticed some very low scores, and it was odd to me. There were some issues about where you started answering those questions. That issue was fixed, raised the overall average quite a bit. You can see those exam statistics reported on the front page of the Canvas with the syllabus pages. So the high, low, average, standard deviation, all that stuff's reported there. I don't talk too much about that stuff in class. You can just go look at those numbers. Again, on the exams, you're basically accumulating points. Those fill up the buckets, and that's how you earn your grade. So everyone in here can earn an A. Those scores are not normalized relative to the class at all. So sprinkled throughout the semester, there'll be bonus opportunities. You'll see them show up in Canvas, pretty easy. Submit it, you get your points, add a little bit more points to your total. So the scores will only stay in zip grade. I'm not going to populate the exam scores in Canvas until the end of the semester. Again, the syllabus has an Excel file that you can start pumping things into to figure out your letter grade trajectory, but keep in mind that file only calculates your letter grade for the entire semester. So it's not calculating it on the total number of points that's current, it's all of the course points. When it comes time for your interim grades, those grades are calculated on the total number of points up to that point in the semester. What else do we have here? Your exam 1, it opens this Wednesday at 12 p.m. So now the exams are basically tracking when the modules end. So again, that'll be through zip grade. It'll look a little bit more like a formal exam in the sense that it was created in a Word document, and I used to give these in class, but now they're just online. So exam 0, as you saw, was basically from a PowerPoint slide deck. So again, that'll be 30 questions, so a total of 60 points. 31 to 40 are bonus points, so 2 points apiece, so there's 2 times 10, 20 extra bonus points you can get on there. Not all the exams will have that many bonus questions, so if there's not enough questions for 40, don't fill in responses for stuff that's not there. It sort of messes with the software a little bit. And thinking forward into May for the final exam, my advice to you as students is to start studying now. And so if you do a little bit each day, each week, you'll be prepared. The final exam in this course is written by the American Chemical Society, and it's a standardized exam. So it's the organic chemistry first semester exam. How many people took general chemistry at USM? So you're familiar with this format of exam, right? You're given a booklet, a Scantron. The organic first semester exam is 70 multiple choice questions. And this study guide exists to help you begin studying for that. It is a separate resource. It's not required for the course, so you do have to buy it out of pocket. You can buy it up in the our school office, which is Tech 430. I think it's like $25. So it's laid out according to sort of the main topics of organic. These sections have like introductory problems where they give you a problem and then a very long explanation. And then after that are the practice problems, so that that 2-column format that resembles the final. And your exam 1 looks like this. So that's how I wrote the questions for these exams. So the 2-column multiple choice A, B, C, and D. That's how most of your exams will look from now on. I can't emphasize enough the weight of the final exam towards your total grade. It's possible that you can go into the final with an A, and that won't change no matter what your performance is on the final. But if you go into the final with, say, a B or a C, you're really going to have to smash this to bump your letter grade up quite a bit. Historically, on the 70-question final, the raw score average is about 21. So 21 out of 70. And that's then multiplied by the number of points, that adds to your total. So again, you really want to do a lot of practice problems in this class so you develop an intuition on how to solve problems. And as the weeks go on, we're going to get further and further away from general chemistry into the new stuff. And that's when students can tend to disengage from learning. So it's important that you keep up, do problems from the textbook. You can find those through the Canvas links. Do them on your tablet, on a sheet of paper, whatever works best for you. But it's important that you do those questions and you do a lot of them. And any questions on that before I get into it? So your exam 0 was on this molecule, AZT. And the reason I like that molecule is because it has a lot of different functional groups in it. And that's what today's lecture is going to be about. This is a toy, for lack of a better word. The model kit that you have for lab looks a little bit different. This is called the ball and stick model. So the atoms are balls, the bonds are sticks, and then these petals or leaf-looking things are lone pairs. So when we look at a molecule, really what it is, it's a collection of different elements with different bonding patterns. So overall, this molecule is called AZT. And then as you saw from exam 0, the therapeutic indication for this is an antiretroviral medicine that people with HIV or AIDS take to help prolong their life. And on the slide, if you notice, it was featured in the movie Dallas Buyers Club with Matthew McConaughey. So these small molecules, does anyone work in a pharmacy tech? You have before?
I was just a cashier then, but I was there.
But back in the pharmacy, if you had to guess, how many different medications or bottles are on all those shelves? A lot.
Like
Over 1,000. And so AZT is one of those 1,000. So those medications come from organic chemistry. These are molecules that do not exist in nature. That they're made by humans, they're made in a lab, and they're made on a large enough scale that customers can go into CVS, Walgreens, and have their prescriptions filled and live healthy lifestyles. So within this molecule, as you saw through those questions, we know carbon, it can form 4 sigma bonds, it can form 3 sigma bonds plus a pi bond. We have red oxygen here, that has a double bond. This oxygen here has sigma bonds. Those are different types of oxygens. And what that's telling us is they're different functional groups. And so we learned about hydrocarbons, which are alkenes, alkynes, and then single, double, triple bonds. Now what we're going to do today, for the most part, is look at when we start putting other elements in there, what functional groups do they form? So your module 1 exam is going to be on understanding how we communicate structure. So can you look at a molecule? Can you identify the functional groups present? What are the hybridizations? What are the bonding patterns? How do the functional groups affect physical properties, melting point, boiling point, solubility in water? So we'll talk about polarity. What does it mean to be polar or non-polar? How can those molecules be miscible in organic solvents versus aqueous or water solvent? So I put this slide up. Sorry. I haven't talked since last Wednesday, so getting refreshed into lecture is always process. So these were the 3 hydrocarbon functional groups, alkane, alkene, and alkyne. And the suffix of those functional groups is telling you the bonding patterns of the carbons. So we're starting with the C2. So we have ethane, ethene, ethyne. So this carbon is sp3 hybridized. This carbon is sp2, and that's sp. And so within that, we have these different shapes. And you can see that by looking at these molecules, the limitation we have on the projector is that it's 2-dimensional, it's flat. But the molecule helps us understand that the hybridization gives it a shape in 3 dimensions. So sp3, we call that a tetrahedral carbon. sp2 is called trigonal planar. And sp is called linear. So within that, we have things about physical properties such as bond distances and bond angles. And that'll be on a next summary slide, but really to help you learn this, I would definitely encourage you as we go through, these exercises and you're studying at home, when you're doing problems, get out your Darling model kit, understand how to use it, and start building molecules so you can see the shapes. When we get into module 3, we're going to talk about a specific form of isomerism, stereoisomers, and that's mirror images. And that can be really hard to understand without a model. How are things mirror images? So here was the 3 structures that I showed you in terms of how this model kit is showing atoms and bonds. What I want to point out, again, the second line here of the double bond that's the pi bond, and it's a cloud above and below the sigma bond. So in the model, this would be the sigma bond. And then we can imagine that lobe and that lobe. So sort of like the bun of a hamburger. Those buns, the top and the bottom, that's the pi bond. And what can be hard to conceptualize because it's abstract, above and below are the electrons, the 2 electrons in that pi bond. So in 2 different places, all at once, all at the same time, are those electrons. The line notation is what we're going to use when we start learning reactions to help us account for where electrons are going when we form new bonds or we break existing bonds. And the sigma plus pi in the triple bond. The two pi bonds are 90 degrees apart, so they lie in different planes. And as you may have noticed already, I'm a fan of setting up tables to help memorize or understand trends. And so this table shows us the different alkane, alkyne functional groups. And as we see in the first column, the hybridization that we're talking about, this percent S character, 25, 33, 50, that number comes from the hybridization. So for sp3, it takes 4 atomic orbitals, 1 s in 3p. So we're taking 1 s and dividing it by 4 total orbitals. That gets us percent S character. That characteristic is important when we learn more about physical organic chemistry and we learn about intermediates that help reactions happen. We can use that to explain the availability of electrons or if they're sort of sequestered. Bond type, single, double, triple. This one, free rotation. It says yes, no, and no. So in our model of AZT here, we have a CH3 group, then a single bond, and then we have an sp2 hybridized carbon. So that single bond, I can freely rotate that. And here we have an oxygen that's double bonded. So notice these lobes. If I hold the molecule stiff, I can't rotate that bond. The pi bond is locking those atoms into place so there's no free rotation. And the same thing happens for the triple bond. The bond length, which is an average. As we'll see in Module 2 when we talk about spectroscopy, the attraction of two elements to make a bond, it's not static or stiff. There's always movement. If you go on to take physics, you'll hear about a concept called 0-point energy. So at 0 degrees Kelvin, when there's no heat in a system, there's still atomic and molecular vibrations. So these things are not stiff, they're constantly moving. And that's another thing that's tough about this class is this model is like a Polaroid picture. You know those instant cameras? You snap it, it prints it out. That's like a snapshot in time. The time is always changing, right? The analogy to this model is stiff. The coordinates are set. But in reality, all of these bonds, the molecule is constantly jiggling and moving. That's because there's always this energy present. So the bond length is an average of the distance as it's moving back and forth, say on a spring. The energy in kilojoules per mole, so we will not be using kcals per mole in this class. We use kilojoules per mole to do some basic arithmetic. You can see that it's increasing from sigma to double to triple because you increase electron density between the two elements. Bond angles are ones that you'll want to commit to memory. Tetrahedral is 109.5. Trigonal planar is 120, and linear is 180. The geometries and the angles will sort of track into the new functional groups that we learn as well. So it's applicable to things other than hydrocarbons. In Canvas, I linked these 3 videos made by Sponholtz, which give you a review of general chemistry, how electrons go into orbitals, how do you generate those electron configurations. And as you watch those, they'll sort of transition into organic chemistry. How do atomic orbitals hybridize? And that's what we see here. And they have some nice animations for it that can, better explain things than I can with just static drawings. It's very visual. They'll show electrons moving, the orbitals forming, and then how they form bonds and molecules. So that's worth your time watching as well. So this is a chart ripped out of a textbook that's talking about orbital hybridization and how that leads to different molecular shapes. Highlighted in green are ones that are relevant to this class. The last 2 rows there are more for general and inorganic chemistry. Because we're studying carbon as the primary element in this class, carbon's not able to access shapes in those last 2 rows. So tetrahedral, this would be your sp3 hybridized carbon. Trigonal planar, that would be your sp2, and then linear sp. These other things, bent, angular, trigonal, pyramidal, those will become important when we start incorporating like oxygen and nitrogen into the molecular formulas. But tetrahedral, trigonal planar, linear, you'll want to have an idea of what those shapes are. Any questions? So on this slide, we'll review hydrocarbon functional groups. And then we might have some questions, but then when we start incorporating nitrogen, oxygen, and halogens, this is going to be, when the fire hydrant opens and you start have to guzzle a lot of information. So alkanes, alkenes, alkynes, aromatic compounds on this slide. And then today you're going to learn, another 15 functional groups. And so again, the functional groups are defined as the specific bonding patterns of the elements. So I say alkanes are fully saturated. That means no degrees of unsaturation. And we were using CnH2n plus 2 as the molecular formula. So let me start over here and introduce these terms. They're almost like directions. If I say, go down Hardy till you hit 49, make a left. It's kind of what we're doing here. Look at the molecule, find a methyl group. What does that mean? So methyl identifies a CH3 group. Another way of saying that is primary. And so that holds true for both the carbon and the hydrogens. So in this carbon count here, we have C5, and that would be then what? H12. We would say that carbons 1 and 5 are both primary or methyl groups. 2, 3, and 4 are all secondary. So secondary is methylene CH2. Now, if we look at an isomer of that, the second structure there, 2-methylbutane, that now has a tertiary carbon with an attached tertiary hydrogen. That's called methine, CH. And even though I haven't written it, you can still classify these. So primary, 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 and then secondary. And the last structure is another isomer, 2,2-dimethylpropane. The new thing there is the quaternary carbon. So that gets the 4 and then the degree symbol. So what do you notice about a quaternary carbon? It has no attached hydrogens. Another way of saying that is it is bonded to 4 other carbons. When we get into Module 2, I'm going to teach you how to think about problems not only from one direction, but sort of from another direction. You'll see a little bit of that today as well. You can explain things one way by what's there, but like what's also not there. And the point of doing that is, again, if you're making a structural claim, you're saying, this data says this stuff is there. The lack of data also indicates these other things cannot be there. So alkenes have 1 degree of unsaturation due to the pi bond. We can describe alkenes as terminal. That's when the double bond exists at the end of the chain starting at carbon 1. Or internal, they start at position 2. And then we saw these geometries. That help us determine on what side of the pi bonds do the substituents lie. Are they opposite? Or the same? Alkynes, 2 degrees of unsaturation, so pi plus pi. And again, those can be terminal, where the triple bond starts at carbon 1, or internal, where it starts at 2 or above. We can also take acyclic chains, bond the terminal carbons together to form rings, and those are called cycloalkanes. So these are, the carbon atoms are saturated in that they have 4 sigma bonds, but the molecule has a degree of unsaturation that is a ring. So again, these would be CnH2n now. And if we start with a ring and further unsaturate it by adding pi bonds, we can get aromatic compounds. And so this is called benzene. It has 1 ring plus 3 pi bonds. So that's a total of 4 degrees of unsaturation. Aromatic, in the common sense of the word, when you think aromatic, you think smell. That's the original sort of impetus for naming these aromatic compounds. Like benzene has a specific smell to it. If you go on to take Organic 2, I'm actually teaching that today in my afternoon lecture. The chemical definition of aromaticity is you look at the structure, you answer some questions through an algorithm and determine, is it aromatic? And that deals with the orbitals involved, not just the physical property of smell. Any questions so far? So let's practice. The molecule shown is called gifratoxin. As you can see in the word, it says is toxin. It's an alkaloid. Alkaloids are naturally occurring molecules that have a nitrogen atom. So when I say naturally occurring, something in nature is making it. So they're called natural products. AZT is a synthetic compound. It's not a natural product. So gifratoxin is isolated from the harlequin poison dart frog. Any biochem majors can read that name for me. What are the hybridizations of atoms A and B? Has anyone ever seen these frogs? If you go down to the aquarium in New Orleans, they have a little frog exhibit. How big are these frogs? They're very tiny. They're pretty cool. I mean, they're like that big. Their whole little display is maybe like this big. And look at their colors. I mean, the color it's fascinating. So the frog does not produce this compound. A plant or a fungi produces this, the frog eats it, and then the frog secretes it. So indigenous peoples will then take their arrowheads and wipe it on the back of the frog. So now the arrowhead has this poison, and they shoot anyone that comes into their territory. So in a sense, I believe this one paralyzes the chest muscles so that you can't breathe. And so you suffocate. So again, as part of my instruction to the class, how do you make this relevant to what you're interested in? You can ask the question, why does this fungi even produce that? Why does the frog eat it? Why do humans then use it? So carbons A and B. What is this functional group called? An alkyne. So an alkyne has a triple bond. A carbon in an alkyne has what hybridization? SP. So we can eliminate A and B. This functional group is called what? Alkene. Carbons and alkenes have what hybridization? sp2. So we can eliminate D and we get C. So like the molecule AZT, which had these other atoms, nitrogen, oxygen, gifratoxin has nitrogen, has an oxygen. That functional group within that molecule is no longer an alkane, or an alkyne. It has another name. So we're going to learn the bonding patterns of those functional groups coming up. So at this point, you should be able to look at that structure and figure out a molecular formula. So that would be the total number of carbons, total number of hydrogens, and then you can visually see the rest of it would be nitrogen and oxygen. So of the total number of carbons, how many are sp3 hybridized? If I can start you off, We already said this and that are SP, right? So we're going to imagine yourself, you've been shrunk in a little machine, and now you're going to walk the backbone. You always want to start at sort of a logical spot where you can get the entire trail. You don't want to start like plunk in the middle or anything. We said these were SP2. Then we get to here, that's SP3. So we're walking the trail. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So B is the correct response. So now think about the different amount of information you're getting from each thing. The molecular formula is telling you the total number of carbon. Then of those total number, you can differentiate them by hybridization. You can further differentiate them by attached hydrogens. Then think about how does the hybridization affect the shape of the functional groups and the molecule in general. So looking at the classes of the indicated carbon atoms 1 and 2, what do you think carbon 1 is? Huh? Secondary. And then carbon 2. Tertiary. So even though carbon 2 is bonded to that nitrogen, the nitrogen's not hydrogen. So we're going to say tertiary. So this would get us D. So yeah, nitrogen and oxygen we're going to call heteroatoms. So when you're doing this type of exercise, just consider that as, say, it's another carbon. So if I was counting 1, 2, 3, I would call that tertiary. So when we're looking at this carbon, we're going to count the number of carbons bonded to it. So if we go to the left, there's 1. We go to the right, there's 1. So I'll put a triangle and then maybe a square, and so that's 2. Any questions? Yeah. Questions? Yeah.
How did you figure out the second degree that
So we're going to move along the periodic table. We talked about carbon functional groups. Now we're going to introduce nitrogen. Then in the subsequent slides, oxygen and halogen. So NH3 is ammonia. And what we're doing is we're taking hydrogens from ammonia and we're going to start bonding carbons to them. So they're derivatives of ammonia. and they're called amines. So that the classes of amines, you focus on the nitrogen and look at the attached number of carbons. So here we have a primary amine. So that has an NH2 group, and then it's bonded to one carbon. So that's primary. If we shuffle that nitrogen into the chain, we see now that there's 2 carbons, so that's secondary. If we make an isomer, there's 1, 2, 3 carbons, so that's tertiary. So of those 3 cases, primary, secondary, tertiary, the nitrogen is showing 3 bonds. Does everyone buy that? So 3 times 2 is 6. What I'm not showing you, but it's there, is the lone pair. If that lone pair were to form another bond, now you have 1, 2, 3, 4 bonds to carbon. That's called quaternary. Now look at what's different. Primary, secondary, and tertiary. I'm saying these are all neutral. But now quaternary is charged. It has a plus charge. So that's something I'm not going to talk about today, but I'll talk about on Wednesday. How do we know it's +1 and not -1 or +2 or -2? So there's a little formula we can use to determine that. If we have nitrogen in a double bond, so now there's 1 degree of unsaturation due to the pi bond. And as I said, this is where you're going to start hearing new terms that are probably going to sound weird to you. But the functional group name is telling you what type of bonding pattern there is. So look at this word here, amine, A-M-I-N-E. If you have nitrogen that's in a double bond with carbon, that's called an imine, I-M-I-N-E. If the nitrogen is bonded to a carbon-carbon double bond, that's called an ene-amine. And that comes from alkene plus amine. If you take 2 terms and jam them together, do you know what that's called? Begins with a P. Yeah, exactly. So sometimes the functional group name will give you sort of an indication, but without seeing the association imine plus carbon-nitrogen double bond, it's not telling you anything, right? You have to have that structural information. 2 degrees of unsaturation is called a nitrile. So you have the sigma plus pi plus pi. So a carbon-carbon triple bond is called an alkyne. A carbon-nitrogen triple bond is called a nitrile. So let me backtrack here. Nitrogen, we're going to call that a heteroatom. A heteroatom is anything other than carbon or hydrogen. So if you stick a heteroatom into a ring, you get a heterocycle. These have 1 degree of unsaturation due to the ring. And by their nature, They have to be secondary or above, because you're having at least 2 carbon substituents bonded to the nitrogen. So there are also aromatic heterocycles, and this will be more of organic 2 chemistry. They have specific names. That's called pyrrole. This is called pyridine. And they're used as reagents for reactions that we'll study. Any questions? So looking at the nitrogen atom in gifratoxin, how would you classify it? So if we circle that nitrogen and then we walk each path out, there's 1 carbon, 2 carbons, 3 carbons. So that's going to be a tertiary nitrogen. So oxygen probably has the most diverse set of bonding patterns, which leads to a lot of different functional groups. So when the oxygen's fully saturated, there can be 2 functional groups. Alcohols. So those are derivatives of water where we've taken 1H and substituted it for a carbon. Or ethers. Now both H's have been substituted for carbon. For alcohols, to classify them, you're looking at the carbon bearing the OH group. So the OH group is called the hydroxyl group. So the carbon bearing that OH group is right there. It's bonded to 1 other carbon, so it's called primary. If you have that carbon bearing 2, that's called secondary. So this last one has 3 carbon groups, that's tertiary. So alcohols, primary, secondary, or tertiary, there's no such thing as a quaternary alcohol. Ethers have 2 carbon groups bonded to the oxygen. So that oxygen is showing 2 bonds. So how many lone pairs does it have? It has 2. So you have CO sigma, CO sigma. If you imagine taking the H from a hydroxyl group and then an H from a carbon that's bearing that hydroxyl group, you can remove H2. That introduces a pi bond, which is a degree of unsaturation. And so that leads to 2 new functional groups, aldehydes and ketones. A carbon-oxygen double bond is called a carbonyl group. carbonyl, carbonyl. If the carbonyl group is at position 1 in the chain, it's called an aldehyde. That means the carbonyl group has an H and then a carbon bonded to it. If the carbonyl group is internal, it has 2 carbons, and that's called a ketone. So now, the next set with 1 degree of unsaturation, we're going to substitute either an H or a carbon on one side and introduce oxygen. And so these are called acid derivatives. So you've heard the term acid. For organic chemistry, this is called a carboxylic acid. So what I'll highlight in red here, that bonding pattern is a carboxylic acid. Sometimes students will call this a ketone alcohol. And maybe you could argue that, but in that bonding pattern, that's its own functional group. It's one thing. It's called a carboxylic acid. You have a carbonyl directly bonded to an OH group, that's an acid. See this hydrogen right here? If you substitute that hydrogen for a carbon atom, now it's called an ester. So if you look at the top there, we talked about ethers. This is a different term, ester. Another functional group, which I'm highlighting in red, is called an anhydride. That's 2 carbonyl groups joined by a single oxygen atom. And then instead of having oxygen, say you had a halogen, in this case you would have an acid chloride. It's a carbonyl directly bonded to a halogen. If the heteroatom was not oxygen, it's not halogen, but it's nitrogen. These are called amides, A-M-I-D-E. An amide has a carbonyl bonded to an amine. So highlighted in red here, there's your carbonyl, then it's bonded to a nitrogen. And these have 3 classes: primary, secondary, and tertiary. And so you're looking at the nitrogen and you're counting how many carbon atoms is it bonded to. So the primary is only bonded to the carbonyl. Secondary has the carbonyl plus another carbon. Tertiary, carbonyl, carbon, carbon. As you can see, this is a lot of information, a lot of functional groups, and a lot of functional groups with carbonyls in them. So the point of Module 2 when we talk about spectroscopy is how do we use instruments to differentiate these functional groups. So Scout's Honor, when we look at infrared spectroscopy, nuclear magnetic resonance spectroscopy, these different bonding patterns all give different signatures in the data you look at. So as you learn to interpret data, you can say, yes, that has a primary amide. But there's some mental sweat equity you have to put into learning how to interpret that data. So cyclic ethers, so these are heterocycles. These are all ethers now because the two bonds from oxygen are to carbon. So those have a degree of unsaturation in the ring. And you can have different sizes. So some of these are used as reagents, some of these are used as solvents. And as the semester progresses, we'll understand the difference between a reagent and a solvent. Aromatic oxygen heterocycles, this is called furan. If you're going on to organic 2, which I will be teaching in the fall, so if you don't like me, take organic 2 at a junior college and you'll have to avoid me then. We'll talk about heterocycles more in depth. And where do these things come from? So furan is actually in corn. So you're eating furan when you eat corn. If you take corn cob, like the whole corn, if you cook it in sulfuric acid, you can distill out furan. Organic 2, we'll talk about what's all this stuff on my can of Red Bull. What are all these chemicals? Why are they in there? But for now, we want to understand the bonding patterns, the functional groups, how do we communicate things? Organic 2 is how do we make it, what is it used for? So this is an alcohol. What class of alcohol is that in gifrotoxin? So there's the carbon bearing the alcohol. It's only bonded to one other carbon, so it's primary. The reason you really want to nail this stuff down now is when we start learning about reactions, say a molecule has 2 alcohols in it. One's primary, one's tertiary. You're treating it under a set of conditions to make a new product. Then you're like, oh shit, I have 2 alcohols. Where do these conditions act upon? The primary, the tertiary, both or neither? And just understanding these subtle structural features at this point will help you rationally predict what product you're going to get. Alkyl halides have a halogen heteroatom. You can have fluorine, chlorine, bromine, or iodine. Notice all of them are showing 1 sigma bond. So how many lone pairs do they have? 3. So I tend not to draw them like on the slide. If need be, I'll draw them on with my pencil here. But keep in mind, they're still there. They haven't disappeared. So primary, again, kind of like alcohols, identify the carbon with the halogen. How many carbons is that bonded to? So secondary, that has 2 carbons. Tertiary, 1, 2, 3. And then as we saw before, if if the carbon is in a carbonyl, so that's sp2 hybridized. Because now it's a different bonding pattern, that's called an acid chloride. Yep. Right here. That's an N.
The little squiggly above it.
Oh yeah, in, IN. So again, when you're looking to identify functional groups, you're looking for those patterns. This one? Questions? So a little bit about how these functional groups affect physical properties. So some of this is a Gen Chem review, but now it's in the context of organic. And for the most part, what I expect out of you as students coming away from this is, looking at these functional groups. If you have like a set of them, like 4 of them, your response is A, B, C, and D on an exam. How are the functional groups going to impact melting or boiling point? So we're going to start this table with water. Everyone knows water, H2O. We know how to figure out the molecular weight using the atomic masses from the periodic table. Oxygen 16, hydrogen's 1. There's 2 of them, so 16 plus 2 is 18. We'll use the Celsius scale in this class. So the weathermen report things in Fahrenheit, so you might have to do some mental gymnastics just to think about Celsius. So does anyone know like room temperature right now? What is it in Celsius? 25 is just a good number to remember. So water, if we're looking at these temperature scales, zero degrees is when liquid water freezes. And so if you add heat, ice will melt. 100 degrees is when liquid water will boil. If you take away heat, the steam will condense to liquid. So 0 degrees is not the coldest thing, though. That's why this thing extends down here to absolute 0, and that's negative 273.15. So that's the Kelvin scale. So the human body, we're at about 36. So we're 11 degrees above room temperature. And so below that scale, I have the red arrow pointing to the right. So that means from here, as you move that way, you're adding heat. And then as you're approaching, and this is something my 11th grade English teacher pointed out to me, and I never really thought about it before then, is cold is not something that's transferred. Heat is the only thing that's transferred. So heat is what moves. Cold does not move. Cold is the absence of heat or warmth. So when you start at 0 Kelvin or minus 273, you're adding heat. But if you're moving towards that 0 Kelvin, you're removing heat. You're not adding cold. So in the phases here, we have solid, liquid, and gas. And just depending on which way you're moving, you have melting, freezing, and then boiling, condensing. So we're sort of calibrated with water in its 3 states. Now, when we get into these organic compounds with the different functional groups, what you're seeing, the molecular weight, you can calculate that. Then the melting and boiling is given to you. The solid temperature range, that's the difference, that exists as the solid before it melts. The liquid temperature range as well. So going from ethane to dimethyl ether to ethanol to ethanal, which is an aldehyde, to ethanoic acid, which is a carboxylic acid. There's the molecular weights. You can never really use molecular weight as a reason for why physical properties change. The things, the melting and boiling point, the data in those columns are directly related to the functional groups present. So I have these terms here: dispersion, dipole-dipole, hydrogen bond donor, hydrogen bond acceptor. Those are the things that affect physical properties. So water is a hydrogen bond donor acceptor. Then you look at ethane, it's none of those. Dimethyl ether is a hydrogen bond acceptor. Ethanol behaves like water. It's a donor and an acceptor. What commonality do you see between ethanol and water? So there's water, there's ethanol. See, they have that in common. So really, to think about it, you're substituting an H for now an ethyl chain. So we can therefore conclude that the hydroxyl group is partly responsible for giving it those physical properties through hydrogen bond donating and accepting. So things that lack, like ethane, they don't have an OH group or something like that. 2 molecules of ethane are not really attracted to one another. But 2 molecules of water, they have that attraction. And so you got to put a lot of heat into the system to break that attraction. So the aldehyde, notice it's an acceptor, but it's no longer a donor. It does not have an OH. It just has a carbonyl. The carboxylic acid has an OH, so it's a donor and an acceptor. And so you can sort of rationalize these differences based on the functional group present. So what do I mean by hydrogen bond donating and accepting? So there's water. I'm putting in the lone pairs. There's another molecule of water. So for these purposes, I'm going to show the attraction as a dashed line. So that lone pair is attracted to that H. That's called a hydrogen bond. And it's a non-covalent interaction, or NCI. We'll get into non-covalent interactions in Module 3. We'll talk really a lot about them in Organic 2. But it's an attraction, and there's an energy there. So to break that attraction, you have to put heat in, which changes the physical properties. So this molecule is called a donor. It's donating that OH bond. And this molecule is called an acceptor, because that lone pair is accepting that OH bond. In the aldehyde case, the aldehyde can only be an acceptor. Notice it doesn't have an H bonded to the oxygen to donate. So if you took that aldehyde and water would be the donor. The aldehyde's the acceptor because it's giving a lone pair that's attracted to that OH. And once you have these sort of attractions, so we know water is aqueous. The aldehyde's organic. You could conclude there, because there's that attraction, that organic molecule should be somewhat soluble in water due to that functional group. Any questions? So we have a couple minutes left. We didn't quite finish all the slides in this deck. We're still going to go over them starting on Wednesday, but in terms of what's on this slide here and in the next slide, I believe. Okay, just this one. So we'll finish up today. The way this is outlined, so yellow, green, and blue, those are increasing carbon count. So under each of them, there's the name, structure, melting, and boiling point. So you have methane, ethane, propane. You can see how adding carbons affects the physical properties. In terms of the columns, if we take an alkane, if we take an H from methane and we substitute that H for bromine, we have a new functional group. Now what you want to think about is how is that functional group, through that substitution, impacting the melting and boiling points? And then down the column, you're just increasing the carbon count. Say instead of bromine, we were looking at how does the OH group affect the melting and boiling point. So those are alcohols. If we put a pi bond between the carbon and oxygen, we have aldehydes. Or if we have the acid. What you'll notice is once you start putting in OH groups or carboxylic acids, the melting and boiling points increase significantly due to non-covalent interactions. And so we're out of time, but when you look at a molecule like AZT, you have all these different functional groups. And so a drug, when it's taken will interact with enzymes based on those functional groups present. And it will give it that therapeutic indication that it's prescribed for. So on Wednesday, we're going to look at molecular formulas. We're going to draw constitutional isomers from them. Then we're going to look at these other things. How do we calculate that formal charge, like plus on nitrogen? How do we look at something called resonance? So we'll do a little bit more drawing, and then you'll have your exam 1 on Wednesday. Start on this slide on Wednesday, but